So, as we are looking at the sustainable grinding solutions in order to give the good environmental effect as well as to give good health to the operators, we have already completed one solution, that is the probable solution is biodegradation of cutting fluids before it is dumping into the river body or the soil bodies and other things. The second solution is to reduce the quantity of cutting fluid, that is nothing but minimum amount of cutting fluid using without compromising the performance of the process. Okay. So, how do we go about the application of minimum quantity grinding fluid? Okay. As I said, cutting fluid or grinding fluid. The probable solution is minimum quantity cutting fluid. The minimum quantity cutting fluid normally will have where you use the minimum amount of cutting fluid. Normally in the flood cooling, where you just drop the cutting fluid by virtue of gravity, in that circumstances it will be 400 to 600 ml per minute. In this one, normally it ranges from 5 ml per minute to so on. It can increase or it can also decrease depending on how much air pressure that you are using, because you have two nozzles, whether it is internal mixing or external mixing, all these things will come up. Okay. So, what you are going to do here is you are making the cutting fluid mist. That means that you are putting a cutting fluid and you are putting the highly compressed air. These two will mix. Compressed air you are going to put and cutting fluid you are going to put. Okay. This will mix and form the droplets. Okay. These are the nano fluid or the mist basically. Mist droplets will fall into the grinding region. This is called minimum quantity lubrication. In particular and in expansion way we will see. So, to avoid the adverse effects of cutting fluid and to make grinding more sustainable, minimum quantity lubrication or minimum quantity cutting fluid technique is a viable alternative. That means that it is an alternative solution for flood cooling process. The minimum quantity lubrication or minimum quantity cutting fluid uses a precision dispenser to supply the minuscule amount of cutting fluid to the wheel workpiece interface, typically in the rate of 5 to 500 ml per hour. You can see here in the flood cooling, normally it will be like 500 ml per minute. Here it will be 500 ml per hour. That means that you are reducing enormously the amount of cutting fluid. Okay. But without compromising the mechanical performance. That means that material removal or the surface roughness and other things. If you see the points literature, over 2 billion gallons of cutting fluid is wasted every year. Okay. It's across USA, across the globe. Normally this amount of cutting fluid is wasted. That means that where this cutting fluid is going, they have to dump somewhere. If 2 billion gallons of cutting fluid is dumping into the river or sea bodies or landfills, this is a drastic and a dangerous thing that people are doing or the manufacturing industries are doing. So, you should avoid that one. 17% of the manufacturing cost is attributed to the cutting. That means that cutting fluid accords approximately 17%. Some places, if you see some of the books, you may find 15%, some of the books you find 17%, 18% and others. Normally the ranges, it ranges from 15 to 17% the manufacturing cost attributed to the cutting fluid, which is at the same time which is about waste disposal accounts for 54%. That is why people what they are doing is just dumping, because to avoid the additional cost of transportation, to avoid the things, to make the post processing of this cutting fluid, to make it biodegradable, then dumping, it also accords some amount. In that circumstances, to avoid and to sell the products at minimal prices, they avoid these things. So, even though you are selling at slightly higher price, if you are helping the nature, if you are helping the other people, that will be good. Okay, what is minimum quantity cutting fluid? Minimum quantity cutting fluid is nothing but you have a cutting fluid, you have a highly compressed air. Okay, both mixes and comes in a droplet or nano size droplet or micro size droplet, atomized mist. Okay, why you are mixing? The convective heat transfer coefficient of the cutting fluid is very high. At the same time, convective heat transfer coefficient of air is very less. Okay. So, but air is a gas, it can enter or penetrate into the seizure zones of metal cutting or the grinding, but as a liquid cutting fluid cannot. So, now we have one advantage, one disadvantage in the cutting fluid, one advantage, one disadvantage in the air. So, now we have to mix the two advantages. This cutting fluid, if you see, the cutting fluid convective heat transfer coefficient is very high, that is a positive. At the same time, easy accessing capability of air being a gas is a positive. So, what we are going to do? We are going to mix forcibly and making the atomized mist. That means that whatever I am going to get out of these is a atomized mist. That means that high convective heat, the convective heat transfer coefficient of cutting fluid is carried by these droplets, and these droplets are in the gaseous form. Okay, atomized mist. Okay, in this atomized mist, what will happen? Convective heat transfer coefficient is retained, at the same time it can penetrate being a gas into the intricate zones of machining or grinding process. Okay. So, as you can see, the cutting fluid mist is coming out of the nozzle and it is going in between the workpiece and the grinding wheel. So, your forced convection will be a, in these circumstances, what will happen? In these circumstances, the forced convection will take place and the heat transfer will be better, so that the performance of this finishing or machining in terms of minimum quantity cutting fluid will be much better compared to flood cooling. The advantages, if you see, environmental friendly and green sustainable, because you are using very minute quantities of cutting fluid. No maintenance cost or the waste, because here mist goes off. There is no recycling or you accumulating in the cutting fluid tank, so that you have to dump after some time. So, there is no maintenance cost because one time use, so you are using it. So, lower thermal shock for the work pieces and tool, that means that since it is a uniform mist which is a gas, since there is no cutting fluid impinging or something, in that circumstances there is no shock and less clogging of wheel grains, because the gas is forcibly impinging onto the grinding wheel. In that circumstances, if there is a clogging of the material because of this force and because of the lubricity and because of the cooling nature, what will happen? This clogged workpiece material will come out of the wheel. So, if the abrasives are very active because of the clogged material taking out by the cutting fluid, what will happen? The good surface finish and material removal will be taken place. As you can see here, the MQL in grinding, the minimum quantity cutting fluid is coming and it is falling, so that the heat which is going out, it will be taken, be it in the chip as well as work and other things. Normally, the basic advantage that you are going to get is the chip loading will be minimum and the active abrasive particles will retain its original sharpness and the surface roughness and MRR will be much better. So, commercially available setups, if you see the commercially available setups, this is a schematic diagram. Okay. So, you can see the mist, how this is a internally mixed mist system is there, where you can see the mist is coming in this region. Okay. So, the cutting fluid as well as the air, compressed air is mixing inside the chamber. This is the chamber, inside it is mixing, then it is forming a mist, then it is forcibly sent out and now you can direct your nozzle at certain distance as per your requirement and certain angle as per your requirement. These are the some other flexible type of nozzles. You can have the cutting fluid as well as the air, and you can mix it and you can send the atomized mist, so that you can have a gas that consists of convective heat transfer coefficient of a liquid, because you are atomizing the liquid. Okay. These are the another setups where you can use the systems. Some are externally mixed, some are the internally mixed, and different setups. These are commercially available at economic price, excluding the compressor. You have to purchase a compressor, then these are these MQL, that is minimum quantity lubrication nozzles, are commercially available in the market. Normally in India you can get at the price around 10,000 or something. So you can, if somebody is interested for doing MQL system for grinding or machining or some other things, you can go ahead with it. Okay. Whereas other types, normally internal mixing, as I said, external mixing. What is internal mixing? If the cutting fluid as well as the compressed air mixes within the chamber, then comes out, that is called internal mixing. If the cutting fluid and the compressed air is mixing outside the nozzle by the virtue of pressure difference and other things, that is called external MQL or external mixing systems. Okay. So, these are the internal mixing systems. You can see here, one input is coming here, another input is coming here, both will mix and come out. This is called internal, and some other places you can see here, two things are externally like this, they may pass on. So, externally mixed, internally mixed, and other things can be. This may not be external also, because just to explain you, I have taken this particular example. So, you can have your divergence and other things. Okay. If you see the 0 degree, that means that if I want at a point cooling or a small area cooling, then you can go for 0 degree divergence. Then the 15 degree divergence, you can have a elliptical type of hole where you can see the maximum range of this will be approximately 15 degrees. Then you can go for 25 degrees. The angle of divergence, you can go for 25 degrees. Okay. Then you can also go for 40 degrees and other thing. Okay. So, you can have as per your requirement. If you are going for a metal cutting operation, you have to choose one type of nozzle. If you are going for a grinding operation, because grinding wheel has its own width. Okay. If that width you have to cover, then you have to go for certain shape where it should occupy complete width. Okay. The thickness will vary. Assume that the thickness is approximately 20 mm. Okay. So, you have to cover 20 mm. If it is 40 mm, you have to cover 40 mm. According to your requirement, you can go for the nozzle divergence and other things. Some other things are there, normally 0 red, where you can go for a small region, then 15 degrees if you have, then you can cover approximately this much region, and 25 degrees and 40 degrees. What will happen if you can see at a one stretch how much space you can cover. Okay. This is the beauty about different. See, now I am giving you knowledge of this type of nozzles, because you have to choose your own nozzle as per your requirement. You may be working on milling, somebody working on grinding, somebody may be working on some other thermal processes and others. I am not talking about laser machining or something. Some of you may be from the design department, some of you may be thermal specialization, some of you may be computational mechanics, if you want to validate the simulations that you have done. So, your requirements person to person will vary, as you know, taste varies from person to person. Similarly, your requirements also vary from person to person. The selection of optimum cutting emulsion concentration. Okay. So, is also one of the thing. Many people normally you bought it, okay, I bought the cutting fluid just mixed with water. No, how much water you want to mix? Water is a better coolant. Cutting fluid, mineral oil is a better lubricant. You have to optimize. You should, as an engineer, you should have quantitative value. You cannot go for qualitative things. Okay. If you see here, water, how do you select? Water is well known to be the best cooling agent. Thus, emulsions, that is a mixing of cutting fluid and water with a higher water content, provide better cooling and partial lubrication. If you are going to mix 20 liters of water with 1 liter of cutting fluid, what will happen? Dominating cooling properties will come. If you have higher oil content in an emulsion, assume that 1:1, 1 liter of cutting fluid, 1 liter of water. In that circumstances, you will have dominating characteristics of lubrication. So, you should not go like that. Okay. In that circumstances, what you have to do is you have to do some preliminary test to find optimum composition. Okay. To obtain better cooling and lubricating performance from the cutting fluid emulsion, optimum quantity of cutting fluid and water mixing should be done at optimum quantities. Okay. So, varying emulsion concentrations, you cannot go by 1:1, you cannot go by 1:20. So, you have to go for the optimum. How do you find that optimum value? For that purpose, there are some standard procedures. See, in this particular thing, this is particularly what we have done for metal cutting in the lathe process, but my intention is to show you how you have to optimize. What we have done in this particular thing is, we have varied from 1:2 to 1:20. Okay. So, 1 liter of cutting fluid we have mixed with 2 liter, 4 liter, 6 liter, 8 liter, 10, 12, 14, 16, 18 and 20. With the basic idea, what you can understand, basic concept shows that water is a better coolant. So, 1:20 will be a dominating cooling characteristics. At the same time, 1:2 will have better lubricating properties, but do I go for it? No, you have to choose. For that purpose, what you have to do is, first thermal property analyzer. What is the thermal conductivity measurement? There is a KD2 Pro thermal properties analyzer is there, where you can find the thermal conductivity of a cutting fluid. Why you have to measure the thermal conductivity? Thermal conductivity, if it is very high, assume that I am doing a machining operation or a grinding operation. If the thermal conductivity of my fluid is very high, that means that it can conduct more temperature or heat from the machining region or the grinding region. So, you can see the thermal conductivity versus cutting fluid concentration. As the concentration increases from 2 to 20, okay, this is the region 2 to 20. In this particular region, what will happen? Once it reaches to 8, this particular point, okay, what it is happening? This is the point. What is happening? The thermal conductivity is now stabilized. That means, if you take any cutting fluid composition after 1:8, it is approximately same value of thermal conductivity. So, from this particular graph, I can say I can go for 1:8 or 1:10, anything I can go, but only thing is that if you use 1:8, you will get better lubricating properties, because you have 8 liters of water. Instead of 1:20, if you take this particular point, instead of this point, the 1.2, here 1:8, it will be having better lubricating properties. Here 1:20, what will happen? Here it will have better cooling properties. Here cooling properties are less, lubricating properties here are less. That is the beauty. So, you can choose any value in between 1 and 2. The second thing is to measure volumetric specific heat. This also will give you how much specific heat it is taking out from the machining region. So, the same composition, 2 to 20 we have done, and you see for the biocutting fluid and mineral oil, which you have seen in the previous class, the compositions. Mineral oil is basically the petroleum product, biocutting fluid is basically a vegetable oil which is commercially available. Okay. So, in these circumstances, the maximum amount of what you can observe is 1:20, because water is a better cooling ability. At the same time, if you take 16, so it is approximately after 16 there is a change in specific volume rate, volumetric specific it is very less. That means from the previous curve, what you can understand is thermal conductivity curve. After 8 you can take any particular value. Okay. So, you have to compromise lubrication, you have to compromise cooling. In that circumstances, if you can go for 1:16, that will be a better composition. Okay. Because you can go for 1:20, but the thing is that lubricating properties will be less. For example, this is particularly for the single point cutting tool, like machining process. If at all people want to go for the grinding operation, they can go approximately 1:12 or something, because you require better lubricating properties also. So, a person can go in between 1:12 to 1:16. That is the best range for a grinding operation. You can see here specific heat of the lubricants, mineral oil is 1.2 and biocutting fluid is 1.4, water is 4.2 approximately. In that circumstances, obviously water is a better one, but you have to compromise or you have to optimize cooling and lubricating properties. That is why you should go in between 1:12. Now, you have optimized the nozzle internal mixing or external mixing, both are good. So, you have optimized the composition. Now, you have to choose which type of nozzle you require for covering for your application. The flat pan, normally you will have a elliptical type of thing. Flat fan even distribution, normally flat pan convex distribution, you will have convex distribution. In the other case, you will have a even distribution, then full cone with convex distribution, full cone with even distribution and other things. Since we are bothered about grinding process will have a wheel like this, which you will have a contact approximately this type of thing. So, you always go for flat fan even distribution, or if it is not available, you can go for flat fan convex distribution also you can go, but preferably second one is the first preference, first one is the second preference. Okay. So, flat pan if you can go, and it will give you better results. For single point cutting tool, people should go for the flat pan with convex distribution, because your area of contact in the machining region or in the cutting tool, normally chip tool interface and other things will have a elliptical shape and other things. If at all you want more details about this one, I have already taught another course, Introduction to Machining and Machining Fluids, where this also is explained, and I am just giving glimpse here. Okay. You can go through that course, it is available on MOOCs, which is recorded at IIT Guwahati. I am very thankful for IIT Guwahati giving me that opportunity. Okay. So, in a metal cutting, your options should be the first one, that is for metal cutting or single point cutting tool, you have to go for convex distribution. In the grinding, you have to go for even distribution. The selection of optimum nozzle spray angle for a machining, you can go for approximately 45 will be the better. As you can see, single point cutting tool here. Where you require always elliptical type of area which has to cover, and if at all you want to go for the grinding operation, the grinding wheel structure will be completely different from the single point cutting tool. So, the better would be like 30 degrees or even you can go for 15 degrees, you can go for 45 degrees, but this may lose some of the velocity that is carrying, that may help you in terms of the dressing the wheel. That means that you taking out of the loaded workpiece material in the form of chips if the structure is open. Okay. So, people nowadays doing some of the simulations, experiments on how whenever compressed air and cutting fluid both are mixing, both in that circumstances how the droplet is formed, what is the droplet size, what is the droplet velocity and other things. We have taken some of the things from our colleagues who are from IIT Madras, Professor L. Vijay Raghavan. So, courtesy to him for sharing his slides. So, what they have done is Malvern analysis is one of the used to measure the exact droplet size, and the droplet velocity was measured using high speed camera. In this particular thing, what they have do is Malvern particle size analyzer is kept here. This is the Malvern particle analyzer. You can see the laser light is coming here, laser light is coming, and the particles, oil mist particles are coming. So, it can measure the droplet size. At the same time, high speed camera is there, and it will measure what is the velocity of the jet. Okay. So, at the same time they have already simulated what is, this is experimental measurement is there, then also people can do computational fluid dynamics to measure various things that required or to validate the experiments. So, numerical simulation, the people they have done velocity versus droplet size. If the velocity is approximately 21.9 meter per second, the maximum size of the droplet, you can see the droplet size, here is the droplet size is this much. If you are increasing to 31.35 approximately, you are going to get a medium size. If you are going to increase the velocity, that means that how do you increase the velocity? Your cutting fluid is constant, you are supplying cutting fluid. So, you are increasing the velocity of your pressurized jet. If you are increasing the pressurized jet, mist formation is taking place. As the pressure increases, what will happen? It will shear the cutting fluid into droplets, micro droplets, nano droplets and other. So, at the same time it will send. That is how the pressure, the velocity increases, at the same time droplet size decreases. You can see here the pressure is 2 bar and flow rate means cutting fluid, how much you are pumping per unit time. So, you are 60, 80, 100. Similarly, droplet diameter if you see 23, if the flow rate is increasing, it is also decreasing. Okay. The same, similarly for the same thing they have increased 60, 80, 100. Similarly, 60, 80, 100 for 6 bar pressure. The cutting forces, normal forces, surface roughness improvement, at the same time temperature, in the better temperature is achieved in this condition, where if you are achieving the minimum temperature, that means that the metallurgical changes of that workpiece is very less. That means that it is very good for the proper machining is taking place in that particular region. Wetting area calculations. Wetting means normally you might have seen super hydrophobic. I have already explained you what is super hydrophobic, hydrophilic. Where hydrophobic means fearing. So, whenever the lotus leaf is there, particle will be there and it will goes off, because it will assume that it will fear. Okay, so to understand in a better way, where alpha is 0, that is wetting angle is 0, which is it is called spreading. Alpha is less than 90, good wetting. Alpha equal to 90, incomplete wetting, and again greater than 90 it is incomplete, and if it greater than 90 no wetting. So, this is how you can make. Normally whenever you have a droplet like this particular angle which is making with respect to surface is nothing but the wetting angle. As I said, if it is angle is theta is above 90 in the figure 2, poor wetting and the good wetting and excellent wetting if theta is 0 degrees. Okay. This is taken from Professor Spencer's, and where he graded, he has done some texturing on the surfaces with a grading wettability. Okay. The wetting angle will be calculated when the droplet of a liquid, which is nothing but a grinding fluid resting on a solid surface to create an interface. The angle between droplet and contact surface outline is known as wetting angle or contact angle. This is the droplet and this is the contact angle alpha. So, wetting ability of grinding fluid on the surface is evaluated by wetting angle, and the wettability of grinding fluids on the surface is one of the important factors because it will substantially affect on its lubrication capability. Because if you see, if this much is occupied, what will happen? This is the how you can calculate the area, contact area of that particular fluid whenever it spread on a surface or whenever you are putting on a workpiece surface. If the wetting ability is very good, it is spreading is very good, that means that it can easily cover the surface, so that the lubrication will be proper. And you can here clearly see here the same thing, 2 bar pressure and mass flow rate, 4 bar pressure mass flow rate, 6 bar pressure mass flow rate. The wetting area, droplet diameters, you can see the droplet diameters. If you are going to increase the pressure of the air, normally droplet size will go down, and mass flow rate also increases. This the droplet diameter is minimum in 100 milliliter per hour and 6 bar pressure. At the same time, wetting area is high, that means that percentage of wetting area is 33%. Okay. As I said, if the droplet size is very less, it can enter, it can penetrate, at the same time it can spread easily on the surface. You can see here droplet size variation with respect to wetting area. As the droplet size decreases, the wetting area increases. The larger wetting area leads to lower grinding temperature because it can easily take out the temperature, not only based on the wetting, it also because of its size. Okay. Surface area of the droplet will increase if it goes to nano size. Both then what will happen? The cooling ability as well as penetrating ability will increase. At the same time, if it is nano, believe me that it can penetrate between the loaded chip in the successive abrasive grains, so that it can deload the chips. The lubrication reduces the cutting forces and cutting energy, while the convection heat transfer and boiling carries the sum of the heat from the cutting zones. That means that it will improve the performance in all respects, from the temperature point of view, from the surface roughness point of view, and cooling point of view, lubricating point of view, all point of view, it will be very good. Okay. Now, we will see the practically what is happening in the figures. Okay. Whenever you are going to give better cooling or the big droplets, whenever you are going to give the small droplets or minimal size droplets, what will happen? Significant plastic flow because of the lubrication effect of MQL is not sufficient tendency in the dry grinding, because A will show the dry grinding of inconel surface. It is observed in the B, this is one done because it is done the dry grinding. Okay. In the second one, hardly any side flow is due to reduced temperature of grinding surfaces on applying the minimum quantity lubrication. Figure B is completed. Figure C, because of the effective penetration of lubrication into the grinding zone and high pressure, it aids remove the chips adhering and other things. Okay. That means that compared to dry grinding, your minimum quantity and the cutting fluid utilization will be always good. That is what the conclusion from the practical point of view. These are the scanning electron microscope surfaces which are done on an inconel surface, which is a superalloy for a in a grinding application, and they are observing how the grinding marks are there, how the morphology is changing, the dry, wet and MQL. Okay. Summary of this class, what all we have done? We have two solutions. One is biodegradation of the cutting fluid, another one is using the minimum quantity cutting fluid. Okay. This is we have studied in this particular class, and overview of grinding and cutting fluid emissions, biodegradation of grinding fluids, BOD, COD, HRT and F by M ratio, that is food to microbes ratio, and other things we have done for the commercial mineral oil as well as biocutting fluid. MQL based sustainable grinding we have seen, and mist droplet size, velocity measurements and simulations. We have measured the contact area by the cutting fluid in the form of mist and other things we have seen, and grinding surface morphology in minimum quantity cutting fluid and grinding. This is about the sustainability of grinding process. Okay. So, hope you understand what is the importance of cutting fluid, positive side, but it has also negative side. So, to avoid these negative sides, we have to find some solutions as an engineers, and these solutions are two. One is biodegradation. That means that you have to treat this cutting fluid before you are dumping into the landfills or before you are dumping into the nearby water bodies. Otherwise, if you cannot do that one, you can go for minimum quantity grinding fluids, where you use minimum amount which is required, and you are pressurizing with high pressure jet. So, forced convection will takes place, and particle sizes are very small and contact area is very good. So, lubrication and cooling will be done, and forced convection will be done compared to your conventional flood cooling, where free convection will be taken. So, forced convection is better than free convection. So, the heat transfer in the grinding zone will be very high. This is about the sustainability and some of the basics of the grinding. Okay. Thank you for your kind attention, and I will see you in the next class.